All right, we're asked to integrate. We have three new integration formulas we can practice. For positive constants a, we have the integral of 1 over the square root of a squared minus u squared du is the arc sine of u over a plus c. We've got the integral of 1 over a squared plus u squared du is 1 over a times the arctangent of u over a plus c. And we've got the integral of 1 over u times the square root of u squared minus a squared du is 1 over a times the arcsecant of the absolute value of u over a plus c. And once again, these absolute values come from the fact we define arcsecant rather, to have a range in quadrant 1 and 2. If we defined the range of arcsecant to be 1 and 3, we wouldn't need those absolute values. All right, in part A, we're given the integral 1 over the square root of 25 minus 9x squared dx. And the first thing we do when we encounter an integral is go back to the most basic formulas we know to see if it fits one of those. This quantity, 25 minus 9x squared, is in a square root, which means it's to the 1/2 power, and it's in the denominator, which means it's to the minus 1/2 power. So you might think to try a u substitution, let u be 25 minus 9x squared, and see if this works out to be a power rule. Well, mentally, or even if you have to write it down, that's fine. Your du would contain an x, which you don't have anywhere up here, which means then we might look at one of these more advanced formulas. And since we have a constant minus a variable quantity squared, that leads us to look at this formula. So to use this formula, we need to identify not only what the u is going to be, but the a as well. So the 25 is where the a squared would be, so we would pick a equals positive 5. And the 9x squared is where the u squared would be, which means we'd pick u to be the 3x. Now choosing u equals 3x means the du is 3 dx, and so this radical I've got taken care of, but I don't have anything left over to go with the dx. So I need to multiply the inside of the radical by 3, or the integral by 3, and I can counteract that by putting a 1/3 out front. So this is the integral of 1 over the square root of 5 squared minus 3x squared, and I'll want the 3 dx there, and so I'll put a 3 out front, 1/3 out front, and so the 5 squared is the a squared, this is my u squared, and that's my du. And so in the land of u, I get 1/3 integral 1 over the square root of 5 squared minus u squared du. And I can apply this formula now with a equal 5, and so I get 1/3 arc sine u over 5 plus c, which is 1/3 arc sine 3x over 5 plus c. All right, in part B, we're given this integral, and we might be tempted to try u equals the denominator. That was one of the substitutions we learned earlier in the chapter. So in this case, the du would be 2x plus 2 dx. We don't have a 2x plus 2 dx, we have a 2x minus 5 dx, but I could actually force that to be a 2x plus 2 by adjusting the numerator here. If I wanted to, and this is one way to proceed, is I could write this as 2x plus 2 in the numerator minus 7. And then I could separate numerators. Like so. Alright, now what do we do with this one now? Well, I could complete the square on this and cross my fingers and hope it turns out to be one of these guys. in arctangent form. Okay, so this is one way to proceed. We're going to go ahead and finish it off this way. We look at the first integral, making this substitution becomes 1 over u du, which is the natural log of the absolute value of u plus c, which would be the natural log of the absolute value of x squared plus 2x plus 5 plus c, which we'll add in later. And now the question is, can this thing ever be negative? Do I really need the absolute values? And I can go over and check out the discriminant of this guy, because if I set m equal to 0, just to see, b squared minus 4ac is going to be 4 minus 20, which is negative 16, which is less than 0. That means that there's no solutions, no real solutions to this quadratic. And since it has a vertex, or not a vertex, it has a y-intercept of 0, 5, that means the graph is always going to be above the x-axis, which means the function is always going to be positive. So I can actually drop the absolute values on that. Okay, so that's going to handle that first part. So now I got to handle the second part. So I'm subtracting the integral, and I'm going to go ahead and complete the square in the denominator. So x squared plus 2x, the leading coefficient of x is already 1, so I just take half this coefficient squared. Now when I multiply him out, I would get x squared plus 2x plus 1. So to complete the square, I would need to steal a 1 from the 5, which means that's going to make it a 4. So you can always check these things, multiply it out, simplify it, you're going to get that denominator. So this is pretty much the arctangent form. I'm going to rewrite 4 as 2 squared, and then the x plus 1 quantity squared. And if I wanted to do a substitution, I've got the a is 2, and I can't use u, I've already used u, so I could use, say, w as x plus 1. The dw and the dx are the same, so I don't need to worry about adjusting any scaling factors, so pretty much I just have a straightforward arctangent. So I've got the 7 there, I can't forget about him. The a is 2, so this would be minus 7 halves arctangent x plus 1 over 2 plus c. And there you get it. So that's one way to do part B.